Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection as usual. Today is a little bit more of a sophisticated topic, so please bear with me and stay with me for a while. So I would like to tell you about hyperbolic groups. So hyperbolic groups is kind of a new topic in mathematics. It's from the 80s of the last century, roughly due to Gromov, basically. So the 80s of the last century, that's really new. So mathematics, like all of the sciences, is growing exponentially when it comes to the number of papers, at least, the numbers of published articles. But still, the 80s is pretty new, right? Just remember how old, whatever, Euclidean geometry is. Euclidean geometry is ancient. So people 2,000 years ago have done Euclidean geometry. Hyperbolic geometry is a little bit newer, and of course, as the name suggests, hyperbolic groups, hyperbolic geometry lies at the heart of hyperbolic groups. We will see that actually. You don't really need to know hyperbolic geometry to be able to follow. It's kind of running in the background. We will see. It's a little bit, it's really nice and geometric in nature, and there will be really a theorem at the end. So most of the time I try to, I will spend to explain what a hyperbolic group actually is. But in the end, there will be actually two nice theorems involved about hyperbolic groups, which is just the tip of the iceberg. So studying hyperbolic groups is kind of a hot research topic. Maybe not hot, but you know, people are still doing it, and there are a lot of questions and so on. It's really cute, and it's the heart of what people call geometric group theory. And if you like those guys, we will see a Cantor sets, which are those very cool, like fractal type of sets, which you might have seen before. So as I said, it's a little bit more of a sophisticated topic. So I would assume that you know what a group is. If you don't know what a group is, this is probably not the correct video for you. So I don't mind if you just stop watching it, of course. So, but anyway, if you know what a group is, if you've seen a group before, you don't need to know too much about groups. But if you have seen a group before, so here is our starting point, kind of a geometric perspective on groups, called the Cayley graph of a group. So the Cayley graph of a group are usually denoted by gamma, is a graph such like this guy. I will explain that guy in a second. And the graph should kind of encode the properties of the group. And how does it work? Well, you choose your favorite group. So this is D10 in my notation. That's a dihedral group with 20 elements. So the 10 is actually saying, so you have 20 nodes. The 10 is actually saying, well, I probably can't draw it. So let me just draw a smaller one. So I would have a D6. Then it would be the symmetry group of the regular hexagon. So symmetry groups here given by, for example, reflecting or rotating in various axes. And it turns out that D6 has 12 elements. So if you have a symmetry group of a regular n-gon, you always have twice as number of many elements. So D10 has 20 elements. Okay, so any kind of group, but this is just my running example to explain what a Cayley graph is. So what do? Well, you just choose a set of generators. This is just whatever kind of words generate your group. So in this case, I could take for D10. So let me do the D6 example again, because I can't just can't draw a regular 10-gon. It will look like a circle if I try to draw a regular 10-gon. So you have two natural operations here. You can rotate in an angle. That's A in my notation, or you can reflect the triangle. The 6-gon or the 10-gon, and that's B. And these two operations generate all symmetries of the 6-gon, and this is kind of general. So they generate all symmetries of the n-gon in general. So you can always represent the n by two number of generators, and then you can cook up a Cayley graph associated to this choice of generators. So the Cayley graph depends on this choice, which is a little bit sad, but it's not too bad. So let's just ignore that it depends on the choice, and I'm going kind of to suppress it from the notation anyway, so it will be omitted. I will just say the Cayley graph, although that's kind of a little bit hand-wavy, right? It depends on the choice. So I shouldn't say I should say a Cayley graph, or a Cayley graph associated to whatever, G, a group, and presentation of the group. Anyway, so this is how it works. Beautiful and simple idea. So you draw one vertex for each element of the group. So my picture upstairs here should have 20 vertices. If I haven't miscounted, there should be 10 around and 10 around. So this is, by the way, my 10-gon. So I can't draw it, as I say, but I can illustrate it using a prepared image. So here's a 10-gon. It's kind of a 10-gon in a 10-gon. And along each 10-gon, I have 10 vertices. So I have 20 in total, of course. And how does the generators work? Well, those these 10 vertices are the symmetries of the tangon. And well, one of them is a rotation, right? So A is a rotation symmetry. That's the green arrow. So A here is the green arrow. And what does the green arrow do? Well, you start somewhere and you rotate along the tangon, right? So it just goes around. You can see a little bit, it kind of doesn't matter. It should be an oriented graph. You can see it a little bit in my illustration. So the arrow that I'm using here is a little bit pointy towards one direction. It doesn't really matter. You can kind of ignore it, but it should be an oriented graph. More importantly, it's a colored graph. So for each generator, I have a color. So my A is also running on the outside because it's a green one, just in, well, on the inside, it's running in counterclockwise direction, I guess, and on the outside, it's running in clockwise direction. And what does the symmetry B do? Well, it kind of connects the two. So here, blue, it connects the two from both sides everywhere. So you should think of one of the operations is rotation clockwise, one of them is rotation counterclockwise, and the way to connect them without breaking the symmetry would be to reflect once and then you kind of turn clockwise into counterclockwise, right? This kind of makes sense if you just think of it, what happens on the whatever 6-gun here or on the 10-gun here. Yeah, that's a Cayley graph. This works for any group. So just write down your generators, so your elements of the group, and you have a generating set, and the generating set will hop you around those vertices, and you just connect them according to where they appear, how they are connected in the Cayley graph. Okay, that's kind of nice. So we can kind of encode the properties of a group in a picture, right? So this looks like, I mean, I really like it. It looks like a symmetry group of a 10-gun. It's a 10-gun, right? So it looks like a symmetry group of a 10-gun. And they might get a little bit crazier. We will see 2 other examples later. But it's a kind of a nice idea, right? So you have a graph associated to a group, combinatorial gadget associated to a group. That's what I thought for a long time. And then I heard about this idea of hyperbolic groups, because it's not just a graph, it's actually a topological space. It's actually a metric space even. So you can define, I will a bit hand wavy here, as I said, suppressing all the details, but you basically can define a metric on the space by measuring how far 2 vertices are away. So here I have 2 vertices and they would be 2 steps away. So the distance between them, no matter what way you go here, so the distance between them would be 2. Okay, so you can define the distance on this graph by kind of measuring how far vertices are away. And you can kind of refine that in an appropriate sense. So you can say this point is a certain number away from this point and so on. Anyway, so you get a metric on the graph. So you can, in some sense, you get a metric on the group. And I can already tell you right now here that kind of this choice of a Cayley graph doesn't affect what I'm going to explain. Okay, so as I said, there's a Cayley graph involved, so a choice involved. It doesn't affect anything, just keep it in mind. Okay, so that's pretty cool, right? You have a group, you have a combinatorial gadget associated to it, a graph, but it's even more than a combinatorial gadget. It's actually a topological gadget or a metric space. So you have a metric space associated to a group. And if you have a metric space, then you can play a lot of games with distances and angles and so on. So let's have a look at a certain really, really cool notion, which if you've seen hyperbolic geometry will remind you of hyperbolic geometry. Okay, so I call it thin triangles. Thin triangles. So I would need to make sure that we all understand now what a triangle is, right? We have a metric space, so we should be able to cook up the notion of a triangle. So a triangle is just a collection of 3 points. So 3 points on my Cayley graph. So here's another illustration of a Cayley graph. It's a very famous one, the Cayley graph of the 3 group into generators. So I have 2 generators here. One goes in this direction and one goes in this direction. Inverse will go. So if let's say this is B, then this is B inverse. Let's say this is A and this is A inverse. So you have 4 directions to go, and the Cayley graph of this piece looks like this kind of branching tree, as you can see it above. Okay, and you can take now vertices or kind of any point on this Cayley graph. You take 3 points, so X, Y, Z, right? That's a triangle. You take X, Y, and Z, and it's kind of a triangle in the sense of this hyperbolic group theory. So in the sense of this Cayley graph. So this doesn't live in our 2, like this triangle, but it lives on the Cayley graph gamma. And this is just how a triangle on this gamma looks like, right? It's kind of the same idea. It's really the same idea as for the classical triangle. The classical triangle, what do you have? You have 3 points and you have the edges between them, x, y, whatever, y, z, and so on. And the last one would be probably x, z. And you do exactly the same thing, right? So you have all of these points, x and y, you have the line between them, x and z, you have the line between them. I haven't even drawn the last one. Of course, you have y, z as well, which is, so the yellow one plus the orange one, that's y, z. So you can talk about triangles in those spaces, and you can talk about distances in those triangles, right? This is kind of a cool idea. So let's recap what we have seen. It's that you associate a graph to a group. The graph actually carries an additional structure of a metric, and now we are talking about triangles in this metric space. This is kind of a very cool concept, right? It generalizes triangles that all of us know triangles, let's say lying in the plane line in R2. And well, what I would like to take here are so-called geodesic triangles. So I don't want to have too long paths, basically. Let's ignore that. Let's say just triangles. And I say they are thin if a certain condition is satisfied. Namely, if I pick a point from x and y, and this should hold for all x, y, z. So if I take a point from x and y somewhere here, then distance between this point and the 2 other points. So here, I take this one, and the distance between this and this edge should be smaller than a certain parameter delta, right? And then I call those guys thin. You will see another illustration in a second, but let's just go with it. So let me draw another picture. Maybe that's nicer. So here is kind of a triangle. It's not the one that lives in here. I will explain in a second why they're all thin here. You pick out a point, and the distance to this and to this edge should be lower than delta, or lower equal to delta. Some delta that we have chosen, some delta greater or equal to 0. Delta equal to 0 is totally allowed, and it actually will appear in this case here because the edge xy in this case is completely contained in the edge yz, so the distance is certainly 0 in this case, right? So here in this example, actually delta equals 0 would work. In general, you could kind of pick any delta. So I say it again. A triangle in this funny hyperbolic space, in this funny metric space, is called thin if, well, a point on one of those lines is just very close to the 2 other edges of the triangle. That's what it says. That's kind of this condition here. Okay, that sounds a little bit abstract, maybe not. Maybe you can imagine it, but anyway, it's always good to have another example to get started. So we also have thick triangles. Not all triangles are thin. So what is a thick triangle? A thick triangle is a not thin triangle. So let's take here. So this is the Cayley graph of Z2. The Cayley graph of Z2 is just the grid, right? So you have points. You can identify them with just the 2 coordinates x and y, and a step above would be x plus xy plus 1. This would get you to here, and a step to the right would be x plus 1y. This would get you to the right, x plus y 1 right. This would get you to here. Right, so you're going to kind of walk along this grid. And that's a Cayley graph associated to Z2, which looks a little bit more harmless than the one associated to the free group, but Z2 is, of course, Z squared, not Z2. Z squared is, of course, much simpler than the free group in 2 generators. But you can now play the same game, right? You have a Cayley graph, you have a metric associated to this Cayley graph. You can talk about triangles. The triangles here look very funny, actually. So since it's a grid, so you would have to choose kind of 3 points, x, y, and z. Here's my illustration, x, y, and z. And well, this is how it looks like. I can't shortcut to z because it's this funny grid. So I kind of need to go this way. So this is my triangle here. It has, again, 3 sides. And you could check here that the condition is not satisfied. So if you take a point here, then those edges move arbitrarily far away, which you can just imagine by taking all of these very, very far away. So if y and x and z are just very, very far away, so this distance here is huge, and this distance here is also huge, then you won't find one single delta that bounds everything, right? So these triangles, they already look very fat. They look like squares. So these triangles are actually fat triangles. They're not thin. Some people call them thick triangles. Some people call them fat triangles. Anyway, they are not thin. So you can't find such a delta that bounds all of them. I say again, why? Because you can you can put X, Y, and Z everywhere, right? So you can stretch them arbitrarily far away, and then those points get arbitrarily far away from all of those sides. So you don't always have thin triangles. You sometimes have fat triangles or thick triangles. It depends on the group. And now we're in business. It depends on the group. So there is something that we can associate to a group, that we can ask a group to satisfy. And that's exactly the condition that defines a hyperbolic group. So we say a group is hyperbolic. Don't worry about the additional words here. A group is hyperbolic if all geodesic triangles are thin. And this really comes from this idea on hyperbolic space. Hyperbolic space is, let's say it's geometry on the saddle, and you can actually see that all triangles look like this. They're really thin triangles, so the angles add up to less than 180 degrees. So they're thin triangles. And now in the hyperbolic space, the condition is exactly the same as before. It's this condition that you are a little bit away here from the other two. It's bounded by delta. And yeah, so this is called the thin triangle condition, or strictly speaking, it's called the Rips condition, but it's equivalent to what people call a thin triangle condition. So if you want to have a look at the various equivalent definitions of hyperbolic group, a link to several very nice expositions are linked in the description. Anyway, so this is a picture for the hyperbolic group. So it's kind of like this. So you have this X, Y, and Z, which now live in my Cayley graph gamma, and you have some triangle in there. And this is what it looks like. Well, it's illustrated here, but let me try again. So you have X, Y, and Z, and you have the various edges between them, and you draw a delta neighborhood around those edges. So here's the delta. It looks a delta neighborhood around those edges looks like you have a lot of balls next to one another. So it looks like for each point you have a ball. So it looks a little bit like this sausage type of construction. I don't really know how to call it. Ellipsoid, whatever. And you do the same for the other two. Then the condition tells you that whatever this is, there should be one delta, which is kind of the radius of those ellipsoids, whatever they're called, and it should cover the whole triangle, right? So the triangle is thin. You can cover it with kind of a little bit thin sausages cover your triangle. And the fun fact about this is that, first of all, you should make sure that this does not depend on involved choices, but it doesn't. It's not quite obvious, but it's also not a very hard exercise to see that this is true. And kind of the fun fact is that theorem here, so one of my favorite theorems, it's absolutely not clear, right? We have discussed two examples here, the thick triangle example, the thin triangle example. It's absolutely not clear how many groups should be hyperbolic, how many groups should have this property. And it turns out that if you appropriately interpret the notion of a random group, then almost all groups are hyperbolic, which I think is pretty surprising in the end. Maybe not, I don't know, but I find it very surprising. Here comes a set of hyperbolic groups. So whenever you have a finite group, like this one, then in the finite group, clearly the biggest triangle, whatever this guy here, would be a triangle. So here's a triangle. Let me see whether I can get this straight. So here's a triangle. This triangle here will definitely be bounded by some delta because the whole group is bounded. So finite groups are always hyperbolic. This is really a notion that you would like to use for infinite groups. But for infinite groups, so this is an infinite group and this is an infinite group, it doesn't appear to be completely trivial which one is hyperbolic or not. And it's certainly usually not. But it turns out that almost all groups are hyperbolic, which is pretty cool, actually. So almost all groups are hyperbolic spaces, if you want, which kind of mimics the hyperbolic geometry, because kind of almost all geometries are also hyperbolic. So it's kind of a very nice there. Okay, and then you can actually talk about the following, which I really like a lot. So you could play around with this right now. Now that you have set it up, you could really play around with it, no problem. You have a metric space, so you can ask several questions associated to a metric space. So you can make sense of a boundary of a hyperbolic group. I should really think about, the picture you have in mind would be you do this Cayley graph construction, and it gets finer and finer and finer, whatever, something like this. This is a Cayley graph for F2. And at one point, it kind of converges to a boundary, which looks like a circle in my picture here. but it's not really a circle. How to define this properly, I won't tell you because I'm running out of time anyway. But we use some kind of geodesic rays, so kind of rays to shoot to infinity. Anyway, you can make sense of a boundary of the space. In this really nice illustration, which is kind of the same as before, but slightly drawn differently, you can already see the hyperbolic kind of the thin triangles here. It's just as a thin square that you see here, but anyway. The boundary is just looks like a circle, but it actually is not. It's a Cantor set on a circle. Maybe that's a little bit clearer if let's draw it again. So here, this is how the Cayley graph looks like. It kind of splits finer and finer and finer in each step. So you kind of won't cover the whole circle. It's kind of a little bit more obvious if I do it like this, and you split it finer and finer and finer and finer, but you only cover a certain type of points on the circle, and it turns out that you cover exactly, the boundary is exactly a Cantor set, not in this classical formulation, like taking something, taking out the middle, taking out the middle of the middle, taking out the middle of the middle. Oh, I can't really draw it anymore, and so on. Taking out the middle of the middle of the middle. This looks very similar. It's just on a circle, right? I just draw, I take out the middle, and I take out the middle of the middle, and so on. So this is this Cantor set arranged on a circle. And this so-called boundary points at infinity, they form also a metric space, and or a metrizable compact space, whatever. And the theorem, another theorem here, really beautiful, is that most hyperbolic groups actually have Cantor sets, or more general, something like a mega sponge, if you want to think about something higher dimensional, as a boundary, which I kind of find very nice. So here we have a connection from groups to Cantor sets, which is kind of a really cool connection. Anyway, let me wrap up. So hyperbolic groups is this funny notion of you take a combinatorial gadget associated to a group, the Cayley graph, you realize, oh, wait, that's not just a combinatorial gadget. You can put a metric on this space. So you actually have a metric space. And you play around with that metric space. You define an appropriate notion of being hyperbolic. Hyperbolic means you have thin triangles. And then you are good to go. You can have the definition of an hyperbolic group. Turns out that almost all groups are hyperbolic. Turns out that almost all hyperbolic groups have a boundary, which is a Cantor set. This is kind of a cool statement in the end, right? So now we have gone all the way in this YouTube video. We have gone all the way from a group to a Cantor set, which is pretty impressive. Anyway, I hope you enjoyed the video, and I also hope to see you next time.